This week, we have Jason Geagan, the National Sales Manager from Manifold Group U.S. Draft Company, presenting boiler venting definitions, theories, and applications. If you have any questions, please feel free to type those out in the questions and answers box. We'd be happy to answer those live or, if possible, at the end of the presentation. But we will do our best to answer those as they come up. With that, I will hand this over to Jason to start the presentation. Thank you very much.
Cool. And yeah, thank you very much, Austin, and to the rest of the DB sales staff for having us. Again, my name is Jason Geagan. I am the Director of Sales, National Sales Manager for U.S. Draft. RM Manifold is our corporate brand. That's basically who pays us. But we go to market under 3 different brands. So today we're going to talk about our U.S. Draft brand. You also may see us as LF Systems. They focus more on laundry, exhaust, and some general building applications. KW is a partnership with Kutzner Weber out of Germany for specialty fans for fireplaces, pizza ovens, that type of thing. So a little bit of background on me. I was basically born and raised in this industry. My father was a licensed plumber in the city of Chicago, which is where I'm originally from. I was way too smart to go to school, so I went straight into the industry and worked my way up from plumbing wholesale warehouse, schlepping 40-gallon water heaters in the snow, and just kind of got up through counter sales, inside sales, outside sales. And throughout my 20-plus year career, most of my focus has been on the boiler room. And so I'll use the word boilers more generically throughout this presentation. That could be a water heater, it could be a pool heater, it could be any gas-fired appliance or solid fuel appliance. In this conversation, most of the time we're talking gas. But so if I use the word boiler and you're worried about water heaters, basically same concepts, just a few minor things. So keep that in the back of your head as we talk through this. Like Austin said, we're going to talk not only about mechanical draft, but we'll also get into just general venting practices, both appliance categories, and we'll talk about some listings. We'll talk about mechanical draft and overdraft, and then we'll also talk about some boiler room safety devices. So when it comes to venting, basically a manufacturer has 2 choices when it comes to getting their products listed. First option is they can be listed as an ANSI Z21 categorized appliance. The other option is to be listed as a UL 795 building heating appliance. Now, very general rule of thumb, if the burner is built into the boiler, it all comes pre-packaged, it's most likely going to be a ANSI Z21 appliance. That's your RBI type products. 795, if it has a external burner, something that can be changed out in the field, that is going to be most likely a UL 795 heating appliance. Now, there are exceptions to those rules, but that's a good general rule of thumb. So the nice thing is that the manufacturers are required to put it on their data sheet or on their sticker, and as well as in their manuals. When it comes to the Z21 listings, they're really creative in naming them, calling them categories 1, 2, 3, and 4. I could read these definitions for you if you'd like, put you to sleep really early in the presentation, or I can just show you this nice little cheat sheet. And this is a sheet that I've actually printed out everywhere I've worked for my staff, because it's a real simple way of determining what your application is, either for the appliance or the venting system itself. And there's only 2 factors when it comes to venting categories. The first one being whether the appliance is positive or negative. Negative pressure is anything that is being pulled out of the appliance. So if Mother Nature or something else is pulling those flue products out of the appliance, that makes it a negative pressure appliance. If it's being pushed out of the appliance, typically by a fan that's being pushed out of the appliance, that will make it positive pressure, okay? And then the other factor is whether the venting system is condensing or non-condensing. Now notice I didn't say the appliance. There are many appliances out there that are non-condensing boilers. The first one that comes to mind is the Futura 2 from RBI. It is a non-condensing appliance, but in certain applications, it can be a condensing flue system, because once that the boiler is not designed to condense, and the Futura 3 is actually the one I was speaking of, excuse me. But that's in that upper 80s efficiency. So where the boiler is not designed to condense inside the chamber, but the flue temperatures are such that they do have potential of condensing in the stack. So that 85 plus kind of 86% is typically what we see as that break point. So if your boiler is listed for 85 or below, you're most likely going to be able to get away with categories 1 and 3. If it's 85 or above, you're going to be in that positive or in the condensing mode for the stack. So again, it really depends on the appliance and the application that it's put in. Now, good news is there's really only 2 listings for categorized appliance. Category 1 is standard B-vent, UL 441. You can buy that at your local hardware store. It's been going on furnaces and water heaters and appliances for years. It's non-condensing, it's negative draft, has tons of limitations. There's an entire chapter in the chimney design section of code that talks about how to size category 1 appliance chimneys. Everything else uses UL 1738 special gas vent. UL 1738 covers 2, 3, and 4. 2 and 4 because of the condensing, 3 and 4 because of the positive pressure. So anything that's listed under UL 1738 must pass certain standards to be able to handle the corrosiveness of condensate as well as the positive pressures of 3 and 4. Now, it doesn't talk about materials in that in the listing, but again, you have to pass these certain tests. So it could be AL294C, it could be 444 stainless, could be 316L stainless. There's even some, it's not really an alloy, but it's a poly blend. It's kind of a plastic, but it's a poly blend that has gone through UL 1738 testings. Anything with that 1738 sticker can be used for special gas vent. Now, the one product I didn't mention having that listing is PVC. PVC is not a listed product for venting applications, so much so that several years back, Charlotte, which is the largest pipe manufacturer in the world, basically said, don't buy our products for that application. They didn't want the liability because what happens with PVC is the melting point, and I'll sidebar and say the melting point, this is not taking a straw with a fire and melting away, disintegrating like you would think. It actually changes the molecular structure of PVC. It does have a kind of a yellowish brown tint to it. And people think you're burning the PVC. That's kind of what you're doing, but really what you're doing is you're changing the molecules to where it's no longer PVC. It's just a very brittle plastic. You can tap it with your knuckle and it cracks. Okay, so, but it goes through no listings, no testings of any of that sort. Now, there is one manufacturer that I've heard of that is tested for very specific applications using a very specific PVC that has been tested to that, but honestly, there are so few and far between applications that it qualifies for. I typically don't bring that up, but again, you can use a polypropylene, you can use various grades of stainless steel, and typically the reason why PVC is used is for cost. Once you get above about 6 inch in diameter, the cost of PVC is actually higher than some of the UL rated products anyway. So kind of takes that out. The other option, or the other side of that, is the UL 795 building heating appliances. These are the bigger appliances, typically your fire tube, water tube, power burner type boilers. And you can see code here that's referenced in NFPA 211. And that uses a different type of material. It's under UL 103. There is some debate or some confusion on this because most power burner boilers are non-condensing and positive pressure. So many people call them a category 3 appliance. That's technically incorrect. That does not fall under a categorized appliance. It does have different requirements because of the temperature ratings. 1738 only goes up to about 550 degrees. UL 103 starts at 1,000 degrees and goes up from there. Okay, so it is a different temperature rating, but it can be made of, again, 316, 304, aluminum galvanized outer jackets, all kinds of different things. It's also pressure tested to a higher rating because your power burners can have higher pressures. Now, it says up here, pressure tested to 60 inches. Please do not put in your specifications to test your boiler vent to 60 inches because it will fail. In order to meet that specification, you have to have no slip joints in the system. That's typically more for generator exhaust and that type of thing. So it also has anywhere from a 1-inch air gap to a 4-inch fiber insulation, depending on your application, the manufacturer that you're using. A whole bunch of things will determine what that is, and Austin and his staff can assist you with that as you're selecting your vent materials. Now, when it comes to sizing gas vents, there's really two things that we look at: NFPA and the ASHRAE handbook. NFPA basically tells us what we can and can't do, and then the ASHRAE handbook tells us how to do it. Now, the first thing that I like to show and kind of make a joke about is that this is the ASHRAE chimney design equation. And usually I ask for a show of hands of how many people have actually seen this, and then even ask more questions about who has actually done this by hand. And the reason I do that is because I was forced to, as a younger man, to do this equation by hand. Now, I wasn't a math major, so it really drove me nuts. But point being is it does work, okay? But there is a problem. As a proud standing member of ASHRAE, I can say this: there is a problem with the ASHRAE chimney design equation, and that's that it's a steady state equation. Okay, this is assuming that your stack is already primed and in operating conditions. It assumes that your BTU never changes. It assumes that your because of that, your flue temperatures never change. Your barometric pressure never changes. Everything is a steady state. And nowadays, we're not selling on-off boilers. Most of the boilers sold today, I would say probably 70 to 75% of what I see are going to be modulating with a minimum 5-to-1 turn down. Okay. So that's obviously going to change the design equation just moment by moment. Okay. But it's a starting point. So we'll use that to start. We also have to determine our pressure loss. Again, a whole bunch of letters, numbers, and symbols. And with that, we can determine our theoretical draft. Theoretical draft is determined by two things. One is the height of your stack, and the other is the delta between ambient and flue gas temperature. So the higher your stack is, the more natural lift that you will get out of that stack, vertical, okay? The bigger the delta is between flue gas and ambient, the more draft you get. That's why it's easier to get natural draft in, say, Minnesota than it is in Anaheim or San Diego. So, so taking those two things and just to show you kind of the difference, this is just a simple single story and a half building. Theoretical draft calculations on a category 1 building, category 1 appliance get you almost about 1/10 of an inch. And a category 4 appliance, it gets you only about 4/100 of an inch. Okay. Now, 6/100 of an inch does not sound like a lot, and it's not really. But if you were to take that and continue to extend it up 3, 4, 5 stories, it can show some issues. And that's what this chart shows here. That basically on a category 1 appliance, on a 50-foot stack, you will overdraft that appliance no matter where you are in the country. Okay. So for years and years and years, we've used mechanical draft devices to control that draft in category 1 appliances. Those devices are called barometric dampers. Okay. So a barometric damper helps soak up excess draft. Okay. So many people that say, well, I'm not comfortable with mechanical draft. If you've been installing or specifying category 1 appliances, you've been using them without even knowing it. Okay. So that's great for 20 years ago when we were using nothing but Cat 1 boilers. Well, nowadays, though, we're moving to high efficiency, high turn down, near condensing appliances. And many times the owner says, well, I just re-roofed my building, so I can't poke any more holes up there. So now I want to take out one big boiler, put in 4 small boilers, and I want you to route it all through this single hole. So that's when we get into common venting. And even if the manufacturer allows that in their manual, as you can see, there are so many variances depending on how many boilers are running, depending on what the firing rate is, whether the stack is cold, whether the stack is primed. So there's so many variances here, and very few boilers can actually handle this kind of a swing. And that's where US draft comes into play with mechanical draft. We offer 3 different style fans. We have our termination style fan, our 2 inline fans. By code, you must interlock to an appliance controller. That's a code issue. And again, we do have all of our UL listings through ETL, both for draft induction and outdoor. All of our motors are standard off-the-shelf motors. We use EC motors, 3/4 horse and above. We're actually moving to 1 horse on the EC motors. Above that, we go to a 3-phase motor, which is an off-the-shelf marathon motor. We try to make it as as easy to service as possible if and when a motor ever does fail. We provide a pre-programmed VFD with the systems, complete system packaging, so that you get exactly what you need for your system. And this is a typical mechanical draft system. This is showing our termination fan as an option. We have our fan up on the roof, our controller on the wall, pressure transducers reading stack pressure here in the common. And as you can see, wires interlock to each appliance. Okay, so a very simple sequence of operation on this would be, once the boiler gets its first call for heat, it sends a signal to the controller. That control sends a signal to the fan, ramps up the fan, it checks pressure, verifies that we are in operation, sends a signal back to the boiler to release the fire. Once that's done, the boiler will go through pre-purge. By code, that appliance has to do an air turnover 3 to 5 times in the appliance before it's allowed to even try to fire. And that's to make sure that any residual flue gases that remain from the previous cycle have been evacuated. So that boiler turns the fan on to pump as much air as it can through its boiler as quick as possible. That's going to affect pressure here, which means my fan is going to react. Boiler turns back on, comes down to low fire, pressure changes, that fan again modulates up and down. And all we're going to do at that point, from the time we start to the time we are completed, is monitor a certain pressure, whatever that is set in the field, to maintain that pressure in this common. Boilers turn on and off, modulate up and down. All we're going to do is maintain that steady, typically a slight negative. Okay. Our termination fan goes up to 19,000 CFM. We don't sell a lot of 19,000 CFM fans, but if you have one, we'd love to help you with that. It is rated for 1,000 degrees. So for high temp applications, we talked about UL 103 being listed at 1,000 degrees. If you have a high temp stack, we recommend using a high temp fan. EC and induction motors. So we offer it in 2 different styles stainless. All of our fans are available in 316L. The reason we do that is because that is a more robust metal to handle condensing applications. And again, UL 705 and 378. Question came up, and I'll back up a slide since it popped in, asking about a drip leg on the boiler's stack, asking if it's good practice. So this is something that is dependent on the system, and it depends on the appliance as well as the vent manufacturer you're working with. All we ask for is that if you're doing an inline fan, which we'll show you in a minute, that we are not your system drains. So your condensate drains are very manufacturer dependent. So you work with, again, with your staff member or your sales member, and they can help you out designing that. So hopefully that answers the question. Our inline fans, we coined the term true line fan construction because our fans are true inline fans. Our T9F shows the X and Y plane, and our straight through fan shows the X, Y, and Z plane. Now, on a new construction, this really doesn't matter. You can design around offsets, but where this is very practical and very, very helpful is on retrofits. We get several calls where they've installed the system. It was supposedly per manufacturer's recommendations, but it's just not working. For one reason or another, they're having struggle with draft. And a project that comes to mind was a job up in Saskatchewan, Canada, where they had installed in the new football stadium up there. They had put in 12 different water heating systems, and each of them were individual, all horizontal. One of them as far as 165 feet in horizontal plus fittings. And the problem with that is that the manufacturer only allowed for 100 feet. So obviously they couldn't fire those. So we actually shipped them 6 of and 4 of the 90-degree fans. And they were able to hang all 6 of the inline fans within a day and a half. Now, they still had some electrical and finish work, but basically all they did was they took out a piece of pipe, a couple of adapters with adjustables, popped the fan into place. They didn't have to rehang anything downstream from that. So it was a great retrofit fan to fix a problem on the fly rather than having to repipe everything, which is kind of why it looks the way it does. It's a little kind of quirky here in the middle. That's to make sure that the inlet and the outlet are basically straight through. Okay, 9,000 CFM. This is rated for outdoors. I have 2 of them on a rooftop. It was the first job I visited when I joined US Draft in 2015. It's on 2 of them on a rooftop in Denver, working flawlessly. Again, 430 or 316L. Our T9F goes up to 16,000 CFM. The design is slightly different on the larger sizes, but it's basically the same concept of a 90-degree fan. Many people use this as their horizontal to vertical transition. Works really well for that. Again, we are not going to be the system drain. We do have drain plugs on all our inline products, but we cannot handle the amount of condensates that's going to be in the entire system. So we want to make sure that we have proper drainage per the venting manufacturer on our system. Now, what about the other side? So we showed you where we needed draft on the high side here, right? But what about overdrafting? What if we're getting too much natural draft? And that typically will happen when the either wintertime where there's a huge variance in temperature, although I think Southern California doesn't have a winter, but in the evenings, when it gets cooler in the evenings, or when the entire system has been running and now we're on the backside where the boilers start to taper off. So now there's less volume, but that stack is primed so much you're going to have some excess draft coming out of that, okay? And that's where we come into overdraft controls. And basically what we do is we put a damper in line to create false back pressure, okay? If as we need draft, in this case, we have both a fan and a damper. As we need draft, the fan will ramp up, modulate up to maintain that negative. As draft exceeds where it needs to be, the fan will actually start to slow down and get down to its lowest speed, and then we'll start to choke it off with the damper. Okay, and those two work in concert with each other so that they're not fighting each other, they're actually accentuating each other. This is a picture of our OBD, multi-blade opposed damper. It's a 2-second actuator, full open to full close, so it's very fast acting. The high temperature model actually has been upgraded to 1,000 degrees, so I got to update that slide. We can give a feedback signal to our controller, and we can also provide a proven open and close auxiliary end switch, so that if you have local jurisdictions that do require anything in line to have an end switch, we can meet that. That's a big thing up in the Northeast where they require mechanical end switches. So 304 or 316L, I can count on one hand the number of 304 dampers we've sold. All of our inline products are manufactured with a raw collar. We can provide a flange adapter to adapt to your vent, or we can work with the vent manufacturer and find out what their adaptation is. They call it a universal adapter. It just slips right onto the raw collar, just like it does onto the appliances. So it really allows for a nice, clean installation in the field. So we've talked about the fans and we've talked about the dampers, and we feel like we're definitely kind of leading the industry in some of the things that we're doing. But where we feel we are next level is in our controls. So the industry standard for years and years has been a negative pressure controller, typically from 0 to 0.6 negative pressure. Okay, that's the range that controller can read and control in. And what happens is, we talked about the pre-purge of that appliance. What happens is that pressure actually will spike during pre-purge, and the controller stops at 0. It's kind of like old speedometers that stopped at 85. That speedometer just stopped. It didn't mean you weren't going any faster. It just meant that it couldn't handle it any longer. So just because we stop at 0 doesn't mean that pressure isn't continuing to rise. So the computer in the controller says, well, we're only 0.04 of an inch away. We're going to slowly ramp that fan up until we can get to set point. And eventually it will taper off and we'll get there. But what we read is plus or minus 1 inch. Okay. So we actually see that spike in pressure. We see that bubble at the top there, and we react much quicker, typically 50 to 60% faster. Now, on a single appliance, this probably doesn't matter because this will happen during that pre-purge cycle. Okay, but what can happen is on a common vent, and this is where I've gotten into trouble in the past with older systems, is you may have the far left boiler here running. System is set at a slight negative. We'll call it an 0.5 inch negative. And everything's running great. But then the master boiler controller says, hey, we need a second boiler to turn on for more heat, for more hot water. So then the second boiler turns on, it does its pre-purge cycle, blows a bunch of cold air into the stack, which changes not only the volume, it also changes the temperature and the pressure. So that pressure actually spikes up, maybe up to a half an inch. And because the controller can't respond to that, it actually creates a blockage in the common vent, which eventually backfeeds and pops the block flue switch on the boiler. The boiler typically will have an air switch on the flue to where if there's a blockage, it will shut the boiler off. So that shuts off boiler 1, but it doesn't block off number 2 yet, so it allows it to go through its pre-purge and fire, okay? But now the master controller says, well, wait a minute, I need a second boiler. I've lost number 1, so let's turn on boiler number 3. So it does its pre-purge. Again, creates another blockage in the common, shuts off the running number 2 boiler. And all of a sudden you have these cycling boilers that can't get going because the second boiler is now, or the boiler next to it is starting to affect that. So there's a couple ways of overcoming that. You can oversize the system to where you have more volume in that header, or where you can put a deeper negative, get that more on the more negative side of the system to overcome that. Or you can just use a controller that can react. Okay. And the other reason we do this, and the thing that really hits home is, we typically don't put a 105-degree thermometer on a 100-degree system. That's just not giving you enough of a range to see fluctuations in the system. So if your typical set point is, say, an 0.5 to 0.10 negative, that doesn't really give you a lot of room on the high side. Now you have plenty of room on the bottom, right? But typically we aren't going more negative than what we're looking for. We're typically going more positive, okay? So there's not a lot of headroom here. With us, we can actually read about the same distance on either side of set point, and then we can react accordingly. Okay.
Hey, Jason, we have
Yes,
another question coming in here from Arash. He's asking, how do we calculate the CFM in each boiler?
Sure. So I'll give you the salesperson's version, and then I can get you the engineer's version in an email. So it's mostly dependent on the efficiency of the appliance. Rule of thumb is anywhere from 1/3 to 1/2 of your MBH. So I actually have my application engineer on the panel with us. So Zach, I'll let you go ahead and respond to that in quote form, or in text form, excuse me. But it's dependent on the CO2 level of the boiler. It's dependent on the efficiencies of the boiler. There's several things that go into it, but rule of thumb is the less efficient the appliance, the more CFM of exhaust that boiler will have. Reason being, you just have more excess air in your exhaust. So hopefully that's the quick answer. Zach, I'll let you go ahead and provide the longer answer in quote, or in text form, excuse me. So back to our controls. This is our V series. We introduced the new V series. We were already a couple of steps ahead of the industry. We've always been a plus or minus 1-inch control system, but we just kind of went next level again about a year ago with our new V series. So it has that EC flow technology built in, bidirectional pressure transducers, high and low pressure safeties. That's the other thing. If you have a system that is constantly got a ceiling, you can't have a high limit pressure, or a high pressure limit, excuse me, because you would be going off on it constantly. Okay, so now with us, we can actually set that limit for, say, neutral or a slight positive on a Cat 2 or Cat 4 system, and now we can actually alarm if the boilers go into too deep of a positive or too much of a positive. And typically, when a fan dies, that's the first thing you'll see, is that positive pressure. Okay, so we have that available, high and low pressure safeties, all fully programmable in the field. There's not one setting in this controller that you cannot adjust in the field, so that we can truly customize it for your application. We also have several different programs we use, meaning that my fan program does not run my damper. I have a fan program, I have a damper program, I have a combustion air program, which we can talk about in another seminar. but each application or each program is built for that application. We started off with our 4-button, simple, inexpensive LCD screen, up, down, left, right, and it works great. It's a very, very cost-effective controller, but if you want kind of next level, we also offer anywhere from a 4-inch to a 7-inch touchscreen, which really gives you a lot of data for the operators. It's really simple for the commissioning agents because all of their data is right there on one screen or maybe a second screen. It really gives them a lot more just visual feedback on how the system's operating. So that's a great option. And then the other thing is Modbus. So when we introduced the V series, that was the biggest request that we were not able to handle, was BMS integration. So we added Modbus communication as standard. And the first question I always ask is, can we do BACnet? We absolutely can do BACnet through a gateway. That's an add-on module that we can provide and program. So why would you use mechanical draft? Well, we showed you a few applications where the manufacturer just doesn't allow it. If you can't common vent that boiler naturally through the manufacturer's requirements, then you need a mechanical draft. But there's also other instances where the vent is fully within the manufacturer's allotment and it fully functions for under code, or excuse me, under design. But we have some code violations. Okay, the first one that I always look to, and this is a big one that we deal with, is I call it the 10-foot, 3-foot rule. Code basically says anything within 2 to 3 feet, depending on what it is, you have, or anything within 10 feet, excuse me, you have to exceed it by 2 to 3 feet. So that's parapet walls, pitched roofs, cooling towers, anything that's in your way, you have to exceed it by 2 to 3 feet. Okay, again, I use 10-foot, 3-foot just to make it simple. Some people ignore those rules and they'll put a curb right on or a cap right on a curb that does not exceed that roof by 2 feet. So that's a common violation. Over here, we call this the Texas Special. In the state of Texas, where we're from, where we live, is a lot of 3-story apartment buildings with single-story mechanical rooms. And what they'll do is they'll take their water heaters and sidewall vent them with V-vent, which is a violation of Category 1 appliances. So we say you can't terminate V-vent on sidewalls. And they say, okay, fine, we'll put a 90 in a piece of pipe with a cap. I'll say, well, that doesn't work because you haven't exceeded this wall here by 3 feet. So then they try and run V-vent up the side of the wall and exceed that. But code says you can't have more than 5 feet of V-vent exposed. So there's a lot of variances that they've tried to overcome it with another piece of pipe, and it just doesn't work. The other solution is just put a fan on each of these and you're done. Same thing with this one. So they cleared this little parapet wall. They forgot about this 12-foot wall on this side. So they could have fixed that. Now this one I just throw up here for just to shake my head at it. That is an exhaust pipe dumping into a makeup air louver. I can't fix that. I would love to know who the contractor was so that I can have their license stripped. But yeah, that's not going to work. So that's just one of those you just have to shake your head. So this is a project actually in Dallas. It was 2 steam boilers. They were installed. They were individually vented. Everything worked great. No issues during commissioning. And 2 weeks later, the rep got a call and said, hey, your boilers aren't running. Get your blank and blank down here and figure out what's going on. So they drive down there and they pull into the parking lot. They didn't even get out of the car. They called the contractor over and they said, hey, where are my stacks? And he says, what are you talking about? He goes, well, there were 2 stacks that came up behind that wall there for the boilers. Where did they go? And they said, well, the director of the property didn't like seeing those, so we took those down. And he says, well, that's a problem because you're not going to be able to run the boilers. He says, well, why not? Because what happens is you get a cross breeze across that parapet, which is the reason for the code. You get a cross breeze and it actually starts creating back pressure on that appliance. So he said, put a piece of pipe back on and you'll be fine. He goes, well, I can't do that. The director won't allow it. He says, well, the only other option is to put a fan on it. Code says we have to be 12 inches above snow line with a mechanical fan. I don't know what it is in Southern California. In Texas, that snow line is 0. I'm guessing LA and San Diego are the same way. But basically, you can now hide this behind that parapet wall purely for architectural reasons. Okay. Now we will also make the boilers probably run a little bit better because we'll provide more consistent, a more consistent draft. But it's really just to hide that vent from behind that parapet wall. If you ever, once they allow everything to reopen and you stop by Disneyland, I'm assuming it's the same as it is down in Orlando, where they spend billions of dollars on architecture, and so they want to hide as much of their mechanical stuff as they can. So they'll actually put this fake wall up, put a fan on it, so now you don't see your vent piping. Another very common one is the 7 times area rule. So you cannot put the largest vent pipe cannot exceed the area. Let's try this again. The smallest pipe going into the largest pipe, the area cannot be 7 times more. And I'm not saying that right. I'm struggling with that. But basically, you can't put a 4-inch pipe into a 32-inch vent, okay? Because the area of 32 inches is more than 7 times the area of the 4-inch pipe, okay? So, and this is a big deal, a real issue in schools, especially older schools where they used to have a big fire tube boiler, and then eventually they just threw in a 40-gallon water heater for the kitchenette that they installed, and then they took the fire tube boiler out to get more efficient boilers in there, but they left the 4-inch water heater going to that stack, and then they wonder why it rots itself out and they're having flue gas issues. It's because the little water heater just cannot prime that stack to get that natural draft. Another one is you can't common vent multiple categories. So you cannot take a category 1 water heater and a category 4 boiler, putting them into the same stack unless you put a fan on it. So in most of these cases, it will tell you you can't do this unless it's an engineered system. And mechanical draft systems actually fall under that caveat of engineered systems because we're providing calculations, because we're doing all of the math. We can prove that our system will maintain that requirement. Good venting practices. So if you're doing mechanical draft, especially, but even in certain common venting naturally, we recommend a common header all the way across the appliances. In this example, on 3 appliances. Reason for that is, especially with mechanical draft, we are going to sense pressure here at the end of the common. And if we did that on something like this, the pressure would actually change with every increaser. Okay, we would actually lose a little bit of pressure. So we would be reading false pressures readings here compared to what's actually going on over here. Okay, so we want a nice common header all the way past that last appliance. Many times what will happen is they'll give us a common header past all of them except for the last one, and then they'll neck down to get that final appliance. I can make that work. It's just not as clean of an install for us for pressure readings, because we actually would prefer to be out of the airstream and actually just read pressure. So that's why we would prefer to have that nice common header all the way across and past that appliance. Another good practice, if you learn nothing else today, learn that lateral tees are your friend. Okay, flue gases are stupid. They do exactly what you tell them to do, direct them where to go. So if you put a bullheaded tee into a system, those flue gases are going to come in, they're going to hit this back wall, and they're going to create turbulence. Turbulence creates pressure. Okay, and what happens is now it creates back pressure and affects everything downstream of that. Okay, this is a branch tee. This is a lateral tee. Okay, so that's actually going to make everything turn and go the direction that you want it to go. And just the easiest thing is, and again, Southern California known for its traffic, right? It's a lot easier to merge onto a highway than it is to go to a stop sign and make a right-hand turn. You can actually get up to speed and get into traffic, okay, with this type of a system, with a lateral tee versus a bullheaded tee. Now, a boot tee is similar. It's not identical, but it is similar. So if you have all of the room to do it, lateral tees are the best option. If you don't have the space, boot tees are the next best option. But in reality, these two are not the same. So if Steve and Austin and his staff, they design a system with lateral tees, and a contractor tries to specify or tries to use a boot tee as a quote unquote same fitting, that is not accurate. Okay, so just keep that in mind when you're looking at designing systems, that a lateral tee and a boot tee are two different things. Okay. Real quick, we had a question come in about common headers. Does it have to be the same? Does it have to be straight? Absolutely not. So we've had many systems where we'll pick up two boilers, we'll 90 degree and grab two more boilers. It does take a little bit more to balance, and we can talk about that actually here in a second. The best way to balance those, but absolutely not. We've had several where we'll have multiple fittings in that common header. All right, so overdraft. So we talked about overdraft and as a system. Everything we've talked about so far has been about the system. It's been about what's going on in this header, okay, based on a sensor location right here, and trying to maintain a certain pressure in this common. Now that pressure is selected. That pressure is selected based on the appliances that are installed. Okay, so for instance, if you have a category 2 appliance that likes to be slightly negative, let's call it 0.02 to 0.08 negative. Okay, that's where the sweet spot for these appliances are. I might set this for an 0.05, maybe an 0.06. Okay, and then we'll determine that based on how the boilers are firing, how we're cycling them in and out. We'll determine how we set that set point. Again, that's all field adjustable. But in reality, what matters is what is actually going on at the appliance outlet. Okay, because that's what matters. The appliance doesn't care what's going on up here. The appliance cares what's going on right here at the outlet. Okay, and so for a couple of years, our engineers worked on a device to where we could now actually do individual draft controls on each appliance. And the analogy that I've used as a kind of a boiler guy is it's going from full flow piping to primary, secondary. Okay, originally we were just trying to keep a flow going up here with the system. Now we're going to try and actually control at each appliance to maintain a certain pressure at each appliance. And that's when we introduced our CDS. It's connector draft system. These are individual draft controls at each appliance outlet. Okay, and it now gives you the flexibility to do a common vent system and run positive on the boilers if you so desire. Many appliances, especially the condensing, really high efficiency boilers, really actually like a little bit of back pressure. And Steve, maybe you could jump in on, I know the FlexCore and the Futura 3. I know those can both be category 2 or 4, if I'm correct. But
yes, they can be category 2 and 4. So yeah, it depends where we set up the combustion, whether we set it up as a positive pressure or as a negative on any of those. And same thing even with the Futura 3s. There's actually a lot of appliances that can do that. Even our Brian and some of our Riello stuff that can be either category, just depending on how we set it up. And then we set the combustion up to match those type of parameters. So if we set it with a slightly positive at each one of the appliances, then we can set the combustion. It's just getting when we set the combustion, we really want the pressure to be constant. That's what gives us that good continued combustion. So
if I could guarantee you that you're always going to be plus or minus 2/100ths of an inch from whatever that set point is, that's going to make your combustion a little bit better, correct?
Yeah, of course. It makes it much more repeatable, and which in turn makes the appliance more efficient.
Exactly. So every commissioning agent that I introduce this to, they want them on every boiler. Now, obviously, there's cost involved, there's logistics involved, but it really allows, like he said, it allows them to now set their combustion, knowing that my draft is always going to be consistent. It's always going to be whatever X is. And what we've done a lot of systems, and this just popped up on the screen as a question, where we'll actually set these as a positive, and then we can either naturally or mechanically size the common for a negative. Okay, so for instance, in my scenario, if I wanted to run these at a 0.05 positive, okay, but in order to do that, I want to maintain a negative here so you don't get any spillage. Now, truth be told, these are positive shutoff dampers, so we don't really care as much if it does happen to go positive. But in order to maintain whatever we want here, this has to be more negative than your set point at all times. It's the only way to do it. Okay, so that might be naturally, or that might be using a fan. Many systems where we'll have the fan pulling this negative, and again, I'll still maintain my certain pressures here, but then I'll set these for a positive. Okay, and it really allows me the flexibility to get exactly what I want at each appliance. This is really critical, or really advantageous when you get. I think of a job in Chicago where they had 3 Category 4 boilers and 4 Category 2 water heaters. So the water heaters wanted to be running at about 1/10 of an inch negative, and the boilers wanted to run at about 2/10 of an inch positive. There's no way you could do that naturally without CDSs. So we actually ran the fan for the entire system, set the dampers for each appliance for whatever they wanted, and then every boiler got exactly what it wanted at the time. And again, this is where the primary secondary mentality came in, that if you had multiple boilers needing multiple flow rates, you would just put a primary secondary boiler on each, or primary pump on each boiler to give it exactly what it wants, and it would modulate based on the newer technologies. You can actually vary flow into the boiler. That's exactly what we're doing here, is modulating at the appliance where it matters to maintain that efficiency, maintain that consistency. And after we released this actually started becoming one of our more popular products, because it can be used in so many different applications. So, Matt, I hope that answers your question there. If not, feel free to follow up on that. But this is the CDS, so this is exactly how it comes off the shelf, fully packaged, fully built in the factory. We do have that Viton seal, so this does meet California's requirement for positive shutoff on each appliance. Again, that same actuator we talked about with our multi-blade damper is now on our CDS, so it's 2 seconds full open to full closed. Controller, all pre-programmed, can be set anywhere from -0.5 to +0.5, so a lot of flexibility for your appliance setup there. And this is exactly how it comes from the factory. All they have to do is bring power, call for heat, feedback to the boiler, and they're done. Comes with a nice 1/2-inch flange adapter. So again, DB sales can talk to the vent manufacturer and say, hey, we're adapting to kind of an industry standard damper flange. Can we get flange adapters for that, blah, blah, blah. So it's a great little system. Question came up, what sizes? These come from 4-inch all the way up to 16-inch. They're not designed to be used as a system damper. I've had several people ask me that, to where they just want to put one in for 3 boilers. The problem is that the control interlock just doesn't have that capability. So we would have to go to our multi-blade with a system controller. So this would be for individual draft control on each appliance. There we go. Real quick, I mentioned combustion air. When everyone talks about mechanical draft, and they think about venting, and they think about getting the exhaust out of the appliance, the most important thing is getting air back into the space, or getting air into the appliance. And so we offer what we call our pressure air system. This is a modulating combustion air system. It takes out the louvers, takes out the big dampers and drives, takes out direct vent, running multiple pipes to multiple boilers. This will actually just dump air from the outside, and it can be either dumped into the space, or can be manifold with drops to each appliance. As boilers come on and off, air gets taken out of that space. Our sensor realizes that, senses the pressure drop, modulates that fan up to put air right back into the space. We're just trying to maintain a neutral. It works really well. It's very cost effective versus large louvers and dampers. Saves you on some security issues, a whole bunch of laundry list of things. So if you're interested in that, again, that's a different presentation I could go into. But it's a great option. Best news is that we can use one controller for both exhaust and combustion air. So it's very, very cost effective in those applications. So just keep that in mind. And then lastly, if I were king of the forest, this would go into every single boiler room. Whether it's mine or not, doesn't really matter. But carbon monoxide is an issue. My LinkedIn feed is constantly fed with CO poisonings in apartments, schools. It's just a continual issue where carbon monoxide is causing, hospitalizations and even worse. So, so we offer our CGM 505. It's a 2-stage CO monitor. It's really specifically designed for the mechanical room because it has appliance interlocks where we can tie in either to the appliance safety loop or through a general building safety loop, like kind of in series with like a punch switch or something that will solenoid valve close a gas valve or something like that. So if it ties into the draft controller, that interlocks to the appliances. That works that way. But it's a 2-stage system. So stage 1 is set at 50 ppm. If it gets above stage 1, it turns on a timer. That's adjustable from 3 to 5 minutes. If it stays above that level for that timer, it shuts off the appliances. Manual reset. If it gets to stage 2, it immediately shuts off the appliances. It's factory set at 100 ppm. It immediately shuts those appliances off. And again, it's a manual reset. So it's really designed to be a safety device to let you know, hey, something is making CO. We're going to try and turn off those devices that are making CO and find out where the problem is. Okay. And again, multiple states are enacting this as requirements in their mechanical space. Texas, effective 2017, made it on all direct vent systems. And I believe in 2021, it's now going to be on all mechanical systems. And for whatever reason, Texas and California like to have this almost sibling rivalry of who can go further with their venting, their boiler specific or boiler requirements. So I am sure California is going to adopt it if they haven't already in certain jurisdictions. NFPA is actually looking at it as a federal mandate. And again, buy mine, don't buy mine. I really don't care. On the CO monitors, I just want people to be protected from CO. Again, I won't go into the details, but there was a story of a technician that passed away because everything that could have gone wrong did go wrong, and he was trying to service the boiler and was CO poisoned within 3 hours. So had this been on the wall, it would have shut the appliances off and hopefully prevented that. But so anyways, add this on. Every quote that DB Sales gets from us comes with the CO monitor because we recommend that on all systems that we supply. So all right, enough doom and gloom on that. Last thing is our sizing calculation. So earlier someone asked about CFM and how that's determined. We actually do those sizing calculations for you. So we will actually, you tell us the type of appliance it is between ourselves and DB Sales. We can determine many of the parameters of the appliance, CO2 percentage, flue gas temperatures, etc. And that will determine the CFM and the pressure drop based on the system layout. We provide this nice report for you. That way, 3 years from now, when you go back through your files, you say, well, why did we do what we did? You say, well, because Jason and his staff told me to, based on this report. So it gives you a nice printout to have for your files moving forward. So with that, pretty much wraps up my spiel. I know there's a couple other questions. Looks like we answered most of them, but if you have any others, I'm willing to stick around for a few more minutes and answer anything we can. And Steve, I guess Steve and Austin, if you guys want to wrap it up.
Yeah, Jason, thank you very much for coming out. We do have a couple questions coming in here. Maybe try to address these if we can here. From Matthew coming in. Would a CDS be coupled with a power vent or I guess a mechanical draft system? Or could the CDS be used separately? Jason, would you care to answer that one? Or
yeah, so I kind of touched on this a little bit, but yes, absolutely. So we've had systems doing both, where we've done it naturally. If the boilers, and this is again rule of thumb, I don't want to get into absolutely all the time, but rule of thumb: if the boilers can handle a positive, we can size naturally without a fan. We can size this common for a neutral. Oversize it, drop some, get the pressure drop down, and size this for a neutral at full fire, we can then run positive at each outlet. Okay. As less boilers are running, it's most likely going to make this more negative. But if it does go slightly positive, you've got that sealed shutoff, so it's not going to blow into the off appliance. Now, if the boiler cannot handle that positive, we recommend putting a fan here to maintain that constant negative, and then set these for a slight negative.
And then the other one, another one coming in, Jason, from another one of our clients here is, what are the sizes of the CDS dampers that you guys have available?
Sure. Yeah, so those are 4-inch to 16-inch in 2-inch. So it's 4, 6, 8, 10, 12, 14, and 16, 2-inch increments. We did have a request for a 7-inch damper. Sure, we could do a 7-inch damper. It's basically going to be an 8-inch damper with 2 reducing bell fittings, because our roll dies just don't go down to 7-inch. So it's either a 6-inch or an 8-inch. So that covers those.
Okay. All right. Well, thank you very much for coming out, Jason. And I think Zach was on here too, and the rest of the U.S. draft team. And thank you, Austin, for putting this together and part of our weekly webinar series that we've been doing here very successfully every week. And thank you, everybody, for coming out. And I don't know if anybody else has any more questions or anything else to add. And otherwise, I think we're good.
Yeah, like I said, I mentioned, if you do have any other questions, I'll put this slide up, and Austin and Tracy, if you guys want to leave this up for a few minutes, I think that's going to be your best source for shoot a quick email over, and they can get it to my staff, and we can answer as best we can. I know, Arash, we've got your email there. I'll make sure that we get that question answered for you.
All right. Thank you all.